Okay. Okay, so optics today, an optical image. Joyce and David and I were all here. I don't know which ones of us show up. Could you say something, David? I know you
Hi,
flat.
hi, David Brainerd here. I might be off on the side of the screen, or maybe I'm not visible.
Right, and I'm in the background too. This is Joyce Farrell. We may not be visible in terms of where our faces are, but we'll certainly make our presence known.
You'll pop in.
Yeah.
I have you up in gallery.
Favorably, if possible.
Yeah.
Right. Okay, so we're going to go through one of the things that has been extremely rewarding in this ISET project that we've had is it gave me a chance, and I know David has done a lot of this also, and Joyce, to learn a lot about optics. And optics are extremely important for the way vision works. I mean, it's not, not just human vision, but all their optics is hugely important everywhere. I remember at the beginning of when we started to develop ISET, we thought, well, we'll quickly get done with the optics and all the interesting stuff will be about sensors and image processing and so forth. And here we are 20 years later with still lots of interesting developments.
So it constantly, I just constantly get amazed, might be too strong, but I'll say impressed how large the effect of the optics are on the initial representation and the consequences of that. Just keeps coming back and hitting us over the head every time we try to move past it.
Right, and then for Brian and I, we're pounded by just and also amazed at the impact that optics has and the creativity and the innovation that's happening there from light field to pixel optics to it's just amazing. It's not really all about optics in
the camera side. It's hugely important
in design of new imaging cameras.
Yeah. Okay, so today's not going to be, it's just the beginning. We're going to make sure that you have a feel. And we're going to start with really old concepts that are fundamental, make sure that we're all on the same page. And, the oldest idea really in optics, and the first idea really was that you could create an image through the use of a pinhole camera. And there probably, as always, there were people who discovered this even earlier, but Da Vinci's notebooks include a description of the pinhole camera. And most interestingly, some reasoning about light itself based on this pinhole camera. And this is a picture here. David and I wrote a paper that includes a description of that in some detail. I'll skip it here, but I've linked to this paper. It's a chapter in a book, and I've linked to it in here in the in this live script that. Yeah.
And maybe we should say we're looking, it looks like we're looking at a live script that called TOI Principles, where this picture is. And that script, does that live in the tutorials directory now? Or okay.
Actually, it's good that you say that. It not only lives in the tutorials, but I have linked it in. Let's see if I can show you where. On the ISETCam wiki page, there's tutorials. And I literally linked it right in directly from the tutorials. It's part of the ISETCam distribution. So there's all
great. All right.
In here, various things, and the principles one that has to do particularly with wavefronts is linked in right here. But there are many tutorials at this point. Some David wrote and some I've been adding. Okay, so this picture, I just enjoy this picture because you can look at this person's toe and we're indicating that there's rays headed in various directions. And what the pinhole does is select some of those rays and the rays will head up here onto this wall. And then there's a point on the tree and there's rays headed in many different directions. And the pinhole again means that only a narrow slice of these rays makes it through the pinhole, and you can see the inverted image on the wall over here, how that would get formed. And this approach is, the first approach to thinking about optics. It's called ray tracing, and in fact, a lot of the stuff that you will see in computer graphics really that just uses pinhole optics to render the images. You have to put in a little extra work and a little extra effort to add the impact of lenses and so forth. And in other scripts, I'll say how to do that from the point of view of computer graphics. But it's very common, and it gets very sharp, nice images. And when you're not worried about the amount of light, because the pinhole obviously is rejecting most of the rays and just letting a small bundle of them through, so that therefore this room on the left is in the dark, and that's important to be able to see this. If there was a lot of light in this room, you wouldn't see the image very well. So
yeah, I would say, just a comment, it's pretty rare that we're not worried about the amount of light.
yes, counting photons is important, and that's very true. So I just wanted to say, even from starting this with this kind of picture here, there are various things to keep track of, like how far away are the objects, how big is the pinhole, how far away is this image plane. There's a kind of geometry. You can see the triangles forming up in this picture right here. And so one of the things that ISET does is keep track of all that. I just put up an arbitrary scene here. I could have put up anything. This scene isn't particularly important, but I wanted you to see that we could put up a scene. The scene, that we're going to simulate over here has got kind of a size, and I'm going to take. So I've created the scene here. Look at the last couple of videos to see about scene create. I'm putting it up in the window. And now I'm going to take this table that shows all the physical properties of the scene that we're simulating, and I'm just going to print it out so we can look at it. And you can see it's got a horizontal and diagonal field of view, 10 degrees horizontal and 14 degrees diagonal. We've only sampled it. It's a very low resolution scene, which just for speed, I did it 128 by 128. It has an implicit size of height and width of 210 millimeters and so forth. It's at 1.2 meters away from the pinhole. And, you can, all these things work together. The spacing of the individual pixels given this other geometry is 1.64 millimeters per sample and so forth. So now that's just a description of the original scene, which you should think of as sort of a description of what we're simulating out over here on this side. And then if you just want to know stuff about pinhole geometry, you're not really worried about blurring or diffraction or any of the other aspects of optics, just a little bit about the geometry. You can create an optical image that's called pinhole, and it's going to turn off all those other parts of the computation. And we're going to, pinhole doesn't really have a focal length, but it's got a distance from the pinhole to the wall over here. So we've used the notation and said we're going to set the optics, so put the wall 1 meter behind. We're going to compute it again. And then I'm going to print out the parameter table, P table for parameter table of the optical image. And you can see, we're kind of skipping the blur. It's a pinhole over here. And we put it 1 meter behind, so that's 1,000 millimeters. It's a pinhole, so the F number is kind of meaningless. We made it a small aperture, one millimeter and so forth. And here are the parameters for that. You can see that the height and width of the image is 174 millimeters by on the side. And the resolution of the samples this is in microns, is a little more than 1,300 microns, so 1.3 millimeters. So
Brian, before we leave this,
yeah.
Since this is a pinhole, the aperture then would refer to the size of the pinhole.
The size of the pinhole, yeah, very small pinhole, yeah, about 1 millimeter. So now, just to give you a sense of what ISETCam does for you, if we say, look, let's move that wall from 1 meter to 1/10 of a meter, let's just move it towards the pinhole and recompute. And here I'll put up the parameter table again. Well, we moved it, remember a moment ago, this was 1,000. So now we've moved it to only 1/10 of a meter, so 100 millimeters. And all these other numbers here have changed also. Now the samples on the height and width has gotten smaller from 117, it's down to 17. The spacing of the samples is much finer. Instead of being 1.3 millimeters, it's now just 136 microns and so forth. Everything changed. So one part of what we always have to worry about and account for when we account for optics is the general geometry. How far away is it? What's the focal length? What's the size of the aperture? How many samples do we have in the image that we're representing? And how will that translate? How will they all cohere? How will they all stay together?
So I think it's worth just pausing for a second. So you focused on the fact that OI recomputed things like, the micrometers per sample and the rest. But the other thing it did is it produced the retinal image. And I think we might have looked at one of those up above, and it doesn't look a lot different. It went by a little fast because it doesn't look a lot different from the scene here because it's a big pinhole camera, and the image being displayed is sort of normalized to the screen. There's actually quite a bit of work done there for you in OI compute beyond just these parameters. It's converting the scene to the image plane, and we don't want to let that just go by unnoticed.
Yes, no, that's very important. And actually, I'm going to confess something that I didn't fix that Joyce told me to fix yesterday, which is it would have been good if I had chosen an example and you'll see one in a moment, in which the original scene and the rendered scene were quite different from one another.
Yeah.
We're going to see that in a moment. It's hard to do that with pinholes because the pinholes are so sharp and they don't defocus, and the only thing that changes is the size, and we're throwing away the size in this rendering. But you're making the right point, and we'll get to that next. A lot of work actually happened here, but we're not. I'm not.
And I'll say that I've never actually created a pinhole object in ISET Bio or ISETCam because the cases we've been interested are actual cameras and actual eyes. But it's actually I was just thinking about teaching, and where I start with a pinhole camera, and I was saying, I have some code that does pinhole blurring. This would be a better way to do it, and it's conceptually a good place to start.
Right. And the graphics, by the way, which we will not get to today, but all the PBRT graphic stuff does have pinhole calculations built into it also.
And you put a lot of effort for making the pinhole into a lens so that it would be more realistic for well, not more realistic, but also just possible to simulate the image on the camera array. Right?
Yes.
Yeah. But anyway.
And so let's move on to the lens, because that's that's where we want to be. And the lens, the big thing about even a simple lens is that it solves a key problem. With the pinhole, it gathers more light. That's not it needs to preserve the image, but at the same time, you want to gather more light. And David's comment earlier is, and I've lived this, is we're always worried, do we have enough photons? One of the things that comes naturally out of ISETCam is you calculate how many photons there are on the image. And as David said, we're always worried about that, and lenses are a way to deal with it, are a way to get us more light, and that's why so many animals have lenses. The complexity of optics and multi-element lenses and all kinds of advanced optics is, not for today, but we're going to deal with basically the simplest approximations to lenses, and these are called shift invariant optics, and we're going to get to that. I'm going to define that and make sense of that for you in a moment. But the number one priority about optics, even before you get to shift invariance, that's sort of the more general property, is quite important, is that lenses, take the light in the scene and make an image. So there's a mapping, and I'm going to call that mapping L for what the lens does. And if you have a scene, and just call it X, but it's going to be a big, hairy, complicated thing with spatial array of different wavelengths and intensities. It's going to be a big, X is the scene. It's a lot of stuff. But the lens takes the scene and creates an image at the sensor surface. And if you have a second scene that the lens will make an image at a second scene. And the thing that makes optics so workable for us is that if you know the image from the first scene and you know the image from the second scene, if you take those scenes now on the physics side, on the scene side, and you just add up the two scenes and say, well, what's that lens going to do? Well, it's really just going to be the sum that you measured for the first scene and the second scene. And that linearity plays a role, everywhere in physics and all kinds of applications. And this is the basic linearity. It's at the foundations of color matching. It's at the foundations of many different things. So used throughout electromagnetic theory. So now the important part for practical matters, the important part about this is that and there are many conditions, the way these optics over certain conditions will behave is even simpler than just saying, well, okay, it adds up. What does that do for me? It adds up in a very simple way, in the sense that if you look at a scene and say, well, that scene is a whole bunch of points, individual points. And what the lens will do to one point, we call that the image that it forms. That's the point spread function, what it does to one point. And if you consider what the lens does to one point and the next point and the next point, and you just look at that function, how far it's spread, if the spread is the same for any point that you would be considering, in other words, it's the same point spread function, and just that it ends up in a different place on the image, but the spread is exactly the same. We call that a shift invariant set of point spread functions. Even though we've shifted the location where we're measuring from, the point spread is invariant. And shift invariant optics are a great approximation over modest regions of many, many optics, many, many places. So if you want to get a good first order close approximation to what we're doing, it's nice to model it as a shift invariant system. We have much more complex, we have shift varying embedded in here and all kinds of other stuff. But for today, we're going to stick with shift invariant and tell you how we handle that, because it's so widely used. In fact, many people listening to this, a lot of them are going to spend the rest of their lives and never even encounter somebody who treats optics as anything other than shift invariant. And that's untrue, but there's lots of really non-shift invariant cases that are important when you get deeper in it. Okay, so now off we go. I'm going to start calculating again, but I wanted to motivate the linearity and the shift invariance.
And just a comment, maybe to just say that a first step away from shift invariance is basically to keep the shift invariance approximation, but change it from one location, say of the retina, to another, and do little patches, each of which you treat as shift invariant. So even as you begin to generalize beyond that situation, it turns out the shift invariant ideas are useful to know as a step, how you might think about generalizing.
In fact, we're now schmoozing about kind of scientific engineering approaches to complex systems, even though the system as a whole is definitely not shift invariant. You can narrow the scope that you're looking at, and that means some systems might not. Yeah, anything not shift.
Yeah, locally.
Yeah, you can look locally and get it there, and then piece it together from lots of little local shift invariant calculations. So I'm going to do a calculation again now, and here we go. So I'm now going to use a different test line that's going to help us see the blurring from typical lenses. And I would say the first, and in some ways the most important shift invariant optics model is what we call an ideal lens, and another way to call it is a diffraction limited lens, or a diffraction limited optics. And usually what we mean by that is an ideal lens, usually with a circular aperture. And this is like the best you could possibly do under any circumstances when you have a circular aperture. And modern lenses can get close to that in some cases, but for various, but they don't always. And for you want other features of lenses as well, for very wide field of views and so forth, that people, zoom lenses, all kinds of things people want out of lenses. And so there are a lot of the lenses that ship with products are not really that close to ideal. Okay, but the diffraction limited lens is always a good one to have available in your toolkit as a theorist, because it sets an upper bound on how good a lens could possibly be. And another really nice thing about diffraction limited lenses as a theorist is that their properties are entirely determined by a single parameter, which is kind of amazing fact. A circular lens and a diffraction limited, its properties is really just determined by the ratio of its focal length to its lens diameter. And that ratio is called the F number. And we can calculate with a closed form what the blurring will be of the point spread function for an ideal lens. And that blur will depend a little bit on wavelength. I'll show you that in a moment. So let's just go do it. So we'll create a scene, and it's called grid lines. And the 512 by 512 samples and 128, a gap of 128 between the lines gave me this little image here to look at. EP means I wanted the spectrum. So every one of these, it shows up as a white line on your screen, but each one of these is a spectrum, and it's equal number of photons across wavelengths. I made the thickness of the line 3, so it would show up on the screen for you. And I said, I want this thing, I want you to simulate something that's not big. I want it to be kind of a narrow field of view. So I set it to be just 3 degrees, the horizontal field of view to just be 3 degrees. And that means that the diagonal field of view is a little bit more than 4. Here's a picture of it. Okay, so now we're going to take this is the world, this is the scene out there, and we're going to create our optical image structure. And this is the first time that you see these 3 letters, WVF, and you'll see that a lot in the ISET code these days. WVF is shorthand that we use for wavefront. And a lot of what I'll be talking about here is thinking about the blur, characterizing it, controlling it, manipulating it in terms of the properties of what we call the wavefront aberrations of the lens. So the lens, the ideal lens, the fractional limited lens, has no aberrations. You're going to see a 0 in a moment. But then we're going to introduce some aberrations, and you'll see the effects. So here we've gone and we've created it. And I wanted it to blur a little bit, so I set the F number to something that I knew would cause a little bit of blur. And so I've got my optical image. I've got it set its F number to 8, and I'm going to go compute. I'm going to take that scene, compute it through the optical image, and usually we let it get a little bit bigger because some of the light spreads. But for this case, I just found that annoying, so I told it, crop that edge. I don't want to see that edge around anymore. And then put it up in the window. And now you can see, here it started out real thin up here. And the blur from the perfect diffraction limited lens with an F number of 8 spread the light out a little bit like this. And all the parameters are shown over here. And you can even see the little bit of color fringing. And that color fringing, which I hope is visible, and you'll see it in a plot in a moment, is because the diffraction limited point spread function depends on the wavelength of the light. And so as we go from 400 nanometers to 700 nanometers, the point spread gets larger and larger. And let me show you what those point spreads are. So remember, it's shift invariant. So that means if I show you 1 point spread, I'm showing you, where it's the same point spread anywhere in the image. And here is the point spread function for 400 nanometers for an F number of 8. And this axis is, space or position in microns. And this axis is space or position in microns. And this particular shape, you see it goes up high and then it comes down, it actually reaches 0 at this black circle over here, which is called the first 0 crossing is also called Airy's disk or Airy's circle. And then comes up a little bit again, and so forth. And this was worked out, what this should be by George Biddle Airy, who's also called Lord Airy. And that's for 400. And now if we look at the same one for 700, you can see it's a little tighter for 400 and a little bigger for 700. And that's why these images a little bit blue in the center and a little bit red on the surround, because the diffraction limit of optics has that little bit of variation. Okay. Another way to plot and to see it is to, what I did here was I said, look, let's take a cut through over here, right through the middle of the image. And let's plot as we go across space what the irradiance is for every different wavelength. So here we go across space. So we're looking at positions in the image from, the center is 0 to the left is negative 100 microns plus 100 microns. This line here is for the blue. And you can see the blue gets up a little bit higher and down a little lower and a little higher over here. And then you can see the fall off and the little bump around the 0 crossing. And as you go from 400 to 700, remember the 700 is a little broader, so it doesn't get quite as high. So you can see from 400 to 700 that the peak comes on down a little bit. And that's why it looks a little bit blue in the center, and the spread over here is a little bigger for the red in for the long wavelengths. It looks a little red at the edge. That corresponds to the blue in the middle here and the red at the edge over there. So that's
great. Can I jump in with a couple points just to expand a little bit?
Yeah.
So first, if you watched the tutorial Brian gave on the scene structure last week, he showed lots of examples of making plots by going to a menu in the scene window. And we mentioned that you could also make the plots at the command line. And I'll just say, although you can't see it here in this OI window, similarly you can make plots from the menu, but then and similarly you can do things like this with scenes, with scene plot. And there's kind of programmatic way and use a GUI way to do these things. The second thing I was just going to say is actually, you've seen there aren't a whole lot of lines of code here to do this. And if you're new to these optics things, it's sort of fun and informative to do things like, well, change the field of view of the image and then see how the relative blur changes if you do that, or change the F number and see what happens to the point spread function and to the total number of photons in the optical image, and these sorts of things. Brian's doing some of them here for us. They're very easy to do in this environment because you've got a top level interface for these calculations, and you can get a little feel for some of how these parameters affect things that I think is useful if you're going to be working with imaging systems.
Exactly.
Right.
Thanks.
And just to follow up on that part, the GUI is a great thing for visualizing and teaching. The scripts, eventually people will come to appreciate the scripts as not just, it's for documentation, obviously, and reproducibility, so that you can come back and see what you did. So both of them are complementary and very useful. And
yes, and here I'll just go and click and make these plots again. Just what David said, and I'm glad for the chance to kind of rerun this stuff. And let me run it again. I'll put it back the way I found it. So I made it 2, and now I made it 8. And you can see how the blur increased, and we get back to the blur there. And as Joyce says, it's very nice to be able to do things like plot just right from here to begin with. But once you get to writing your paper, you want to get away from clicks. You want to have it in a script for reproducibility. And Joyce's point is that's a way we live our lives. Okay, so now I'm going to get to the next level of complexity. Suppose that you have a system that is not perfect, and you might know something about it. And in particular, there's one way that people communicate about the quality of the lens is to specify its wavefront aberrations. And if it was perfect ideal lens, okay, 0 aberrations. But lenses can also be described in terms of how aberrated the wavefront function is as a point near the center comes to form an image. Instead of having a perfect spherical converging wavefront, maybe you have some deviations from that perfect sphere that would come down to a point. So, and in fact, in recent times, we have been relying, I checked, David, we started doing these wavefront calculations about a little more than 10 years ago, but we really only put them front and center in the code probably a year or 2 ago. We kind of migrated into them, and that's how that goes. So at this point, a lot of what we do is centered on controlling the parameters with wavefronts. And partly this is because we just thought it was a good idea. I'll show you some examples. And a lot of it came because David and Nicholas had done so much work with the human eye, and people who work on adaptive optics communicate about the properties of the human eye as if they are largely in the center, shift invariant, and they will tell you the wavefront aberrations of living human eyes. And so that makes a real natural way for this code to segue into ISET Bio, which David will produce the next video about then. So we have the ability to go, this is our go-to move at this point. We create an optical image that's going to be controlled by a wavefront. In fact, you already saw me create one that was pinhole that had no blurring. Now I'm creating one that's going to be able to have blurring, diffraction limited, or even more aberrated by controlling the wavefront. There's a third one I will not get to that includes yet other factors, shift varying point spreads, and yet another one after that that includes 3D calculations. So there's a set of these further, but today we're just going to go through the wavefront aberration one. And so, once you create that, you can ask yourself, okay, what lens did this guy create for me here? And for this particular lens that I created, it's, in humans, we're kind of used to having eyes with about 60 diopters of focus, but people who build cell phones have very short focal lengths. And the dioptric power, the focusing power is typically much higher in order to make those cell phones very thin. So for this particular one, it's nearly 260 diopters, so it's very, very powerful. And we can say, okay, you know what, maybe this, what would happen for this image with this nearly perfect lens, but maybe I got the focus wrong. Maybe I've got an algorithm that's trying to focus my lens on a nearby object, and I'm off by a little bit. Maybe I'm off by, out of 258, maybe I'm off by 15 diopters. What would my point spread function be? So I can set the defocus, and then this is, you'll have to, please excuse me, I'm just going to stick it in here. Z coefs stands for the Zernike polynomial coefficients that describe the wavefront aberrations. And in this tutorial, I'm sorry, I'm not going to be able to go into all of the Zernike polynomials and their wavefronts and so forth, but that is available. That's a whole other tutorial over here in which we describe them and go through the calculations. And in fact, there are several of them. I just can't do everything. And here's the whole parameters for it and so forth. I just can't do everything at once in this particular tutorial. So, but the way we control the wavefronts and what its imperfections are by setting the parameters of the Zernike polynomial coefficients. And those are the polynomial coefficients that when you watch Austin Roorda or Dave Williams or Alf Dubra or any of these guys tell you that they've measured the Zernike polynomial coefficients, this is what they'll hand you for the human eye. So I just modified it. I said, well, okay, I want this this wavefront one. I want the coefficients. I want the defocus. And here's the amount, and here's which parameter it's going to be in the polynomial coefficients. And I'm going to set it there. And that changes. Now you can see we've got a somewhat different shape of the point spread function. And in case you're wondering, what are the possible coefficients that you can that you can set? That's again in the other tutorials, and they have names like piston, vertical tilt, horizontal tilt, and so forth. And defocus is a simple and important one. And you can see how nice it is that we can just blur this out a little bit by some controlled amount just by setting the defocus right here and plotting it. And when we do,
no, go ahead. Say the one we do, and then I'll come back.
And when we do, we go get this. Here's the rendered image. So it's rendered in this with the defocus. It looks like this. Notice it's not quite as colored. All the wavelengths are defocused by the same amount. And it just, looks a little bit different. And well, actually, they're all defocused so that you don't see the difference as much. I should say that the defocus is still wavelength dependent. I shouldn't have introduced that. It is still a little bit wavelength dependent, just doesn't show up as visibly here. And here it is at 400 nanometers, and here it is at 700 nanometers. Just got a little different look from the perfect one that we had before. And as a result, when you render it, it looks more like this instead of like the red and blue that we saw before.
Could you go back up to the OI set?
Yeah.
So something you have to think about, and you probably have it right, but I always have to go look at the documentation and be careful, is the units that go with these Z coefficients, because there's a place in the code where they all get converted to microns.
Yes.
And so whether you set them in diopters or whether you set them in microns is something, as I say, I can't remember, but is important to get right.
Yes.
And
yes, and my understanding is that defocus is set in diopters and everything else is set in microns.
Right.
That's my current understanding, and I will delete this video if I'm way off on that.
Yeah. And that could be right for the special case of that. If you're clocking in a vector of Z coefficients, then I think you have to convert the defocus to microns if you're not using the defocus key value. But again, that's probably laid out in one of these other tutorials. And I'll just say for now, you have to think about it carefully when you're doing a real calculation.
Well, if somebody's watching this for the first time, take David very serious on that. I believe I got this right, but I make mistakes all the time. And I believe what but it's entirely possible that I'll have to edit it. I know the others are in microns, and we'll get to, and we're almost done. We're going to change a couple of others just to see what the effects are. So, so here's the defocus. Remember how it looked before, and now it looks, broader. This one looks even broader. And you can set the Zernike coefficients en masse. So I'm going to actually, in these next couple, I'm going to set both the defocus and these other two, because I'm kind of into showing you astigmatism. Astigmatism means that it's no longer going to be a nice circular point spread function. It's going to have a blur that's prefers slightly different orientations. So I'm going to start out just by setting them all to 0. And that's going to get us, which is what I did here, and then plot it. And that gets us back to our perfect ideal lens. And then I came down here and I set this to 20 microns of vertical astigmatism, but no oblique. And you can see how these blurs are kind of oriented along the principal axis. And it's okay. So now we've got a little control of kind of an asymmetry. These numbers can be negative, by the way, which is, gives more flexibility. And then now I'm going to change the oblique. So 0, 0, oblique, and that's going to go in here. And the cell array was the names. Remember, it was the names, defocus, vertical, oblique. And so that's what's coming in here, defocus, vertical, oblique. That's the names of them. And we plot it. And now you can see that the big blur is kind of oblique as the name. We didn't make up these names. These are names that are standards by the international optics community. So that gives you a sense, this is a nice way to plot, to control the point spread functions and to let you both take information from manufacturers or from people measuring the human eye and stick them in there if they give you those values, and create the proper point spread functions. And they can be and they are wavelength dependent in ways that you can also control. And then the final point, the last thing I'm going to say for today is I've been talking about these lenses up to this point as if they all have circular apertures. But it's possible also to say, you know what, I know what the wavefront aberration is, but I'm going to put an aperture in there that has some other shape. Maybe it's going to be like the slit of a cat's eye, which is something I'm planning to do before long. It's going to be oriented one way versus the other. Or the case I'm going to show you is the case that we worked on for cameras. For classic cameras, instead of many of them have, maybe some of you have seen this, they have these kind of array of blades that go around the camera. And when you open them up, the blades shift away and you end up with a polygon around the aperture. And those are pretty common. So if you say we can create different apertures and put these apertures on the wavefront aberration function. So not just the wavefront over the circle, but we can actually block out parts of it. Maybe in this case, we're going to block out make it a polygonal aperture, a set of bounding lines. And so to do that, I'm going to create this scene. It's a very high dynamic range scene, which is going to let us see the blurring of the apertures. You'll see it in a moment. And we're going to go create a fresh optical image. I did that here because I wanted to say that when you create it, the wavefront is so important that sometimes we create it, get the optical image, but we just want the wavefront struct itself. Just go get me that wavefront struct. And so I created it that way. Again, from the other tutorials, I wanted a high resolution rendering, so I increased the resolution. This typically, I think by default is 64, and I just wanted it to look a little nicer, so I increased this. And now I'm going to go make a series of apertures. So I'm going to have 4 sides, 6 sides, 8 sides. 0 means it's a circle. And I'm going to go, for me, it was fun to go and do this, to visualize it. I could have just stopped here in the optical image and shown you the pictures there, but I made it for 4, 6, 8, and 0. And I took it all the way through because I want you guys to know that we can and do take it all the way through. Imagine we had a sensor, and then we took the sensor and we image processed it, and then we showed you the image for that. And these are the images that we would compute with the these are the images that we compute with these polygonal apertures. You can see that you get 4 main lines if you have a 4-sided aperture. If you get a 6-sided aperture, you get this. 8-sided aperture, you get that. If it's circular, you get that. These other little incidental things are because I put some scratches and dots and dust and so forth into the aperture. So it's not perfect lines. If I got rid of all those, it would be perfect lines. But to make it a little more realistic, you can see the effects of the scratches are really coming out over here, and they're visible over here. So the main thing I wanted you to take away was that we have now in the core of ISETCam the ability to specify both the wavefronts and the aperture shape. to do, and even to put little scratches and lines and dust and so forth into the apertures, and go all the way through and render fairly complex images. And in this case, it's a very high dynamic range image that I'm compressing using the Adelson algorithm so that you can see it on the screen.
So Brian, for these images, the three on the left would be images. So for example, that might fall on a camera array due to the aperture and scratches on the lens of a camera, right? And for the human eye, this is a question actually, human eye is a circular aperture, so it'd be closer to the one on the right?
Yes, though, you know, it's an interesting, I've never actually, maybe David has, I've never really looked at people's actual pupil shapes and how perfectly circular are.
Well, it's biology, so I'm sure they're not perfectly circular, but they're more circle than they are hexagonal.
Yeah.
But the other thing about the human eye, there's an interesting thing which isn't really in the pupil aperture, but which you can model that way, goes under the fancy name of the Stiles-Crawford effect, which is that light coming from different parts of the pupil is not equally effective in stimulating the photoreceptors because of wave guiding properties in the photoreceptors. But the easiest way to model that is not to do it photoreceptor by photoreceptor, but rather do it by a kind of Gaussian, circular Gaussian kind of aperture, or an aperture of a continuous shape. But using this apodization facility is just a computationally more convenient way to do that. Which,
right.
In the human case, we can do it.
And that's a good connection to the human. Yeah, that makes a lot of sense. And we could we'll have more other little tutorials about connecting to things like the Stiles-Crawford effect and creating different, how do you create apertures? How do you create apertures with different shapes? How do you compute with them? This is kind of a high level overview of, you know, facilities that we have for doing these calculations. We haven't really dived deep in, but you can see that we created an aperture and it had based on various parameters and so forth. And there's all kinds of ways to create apertures in principle.
Just so I don't confuse people, sometimes you might actually look at a headlight, for example, and it would look like one of these stars, and you might, oh gosh, is that due to the aperture of my eye? But actually that's due to the shape of the headlight. So just for a point source, it would look more circular. I didn't want to confuse people with my question, actually.
Yeah, you get these kinds of, so this is often called flare, what Joyce is pointing at, that you can get these effects sometimes because of your eye, and sometimes you can get them because of other pieces of glass that are in the way, like the glass at the front of the car, the glass in front of the headlight, and other aperture effects that are present in the scene. But I look mostly so this is Joyce and David and I enjoying the moment. But mostly I think we should wrap here and just say, look, we went through a bunch of stuff all the way from pinhole and the considerations of geometry. And, you know, we've been keeping track of the geometry all along, and the fact that we're blurring, we could blur just by an ideal amount, or we could blur by amounts that we, you know, control in terms of vertical, oblique astigmatism, defocus, and so forth. There's a bunch of things that we can do, and we can even control the shape of the pupil and put little scratches in the pupil and lens and such, and get fairly complex images. And we could go even further, but it's time for us to stop.
Great. And next time I will build on this this material to sort of basically to talk about the z-coefficients that we use when we model the human eye and how we adjust those and other parameters to match up to the human eye, and particularly its chromatic aberration, all of which is in this code, but the kind of parameters are somewhat different for the eye, and we use that to compute the retinal image. So we'll do that in the next one.
That's great, and it's my favorite bit, and I really resisted putting it in here because what was it? We always used to say that the largest aberration in the human eye is chromatic aberration, And I didn't say anything about, I just, hinted there, but David's going to take us home on that. So great stuff. Okay, thanks. See you guys.
Bye.